Hello everyone. So, today we will start module 3 finite difference method, and in today's lecture we will learn finite difference by Taylor series expansion. In last lecture we have learned the classifications of partial differential equations, and you have seen that in heat transfer and fluid mechanics problems there appears first derivative and second derivative of dependent variables. The differential of dependent variables appearing in the partial differential equation must be expressed as approximate expression, so that a digital computer can be employed to obtain a solution. So, for that purpose let us take one function f x. So, we will use finite difference method. So, there are many ways to discretize these partial derivatives, but in today's lecture we will use Taylor series expansion. So, let us consider any function f x. Okay. It is a continuous function. Now, we need to find its derivative del f by del x and del 2 f by del x square using this finite difference approximation. So, before doing so we need to have discrete points, or we have to divide the domains into discrete points. So, those points generally we represent by index I in x direction and j in y direction. So, if we consider one dimensional domain, so if we discretize into discrete points, so these are known as grids. So, this is one point, this is one point, this is one point. So, these are the discrete points and separated by a distance, uniform distance delta x. Okay. And these index of these discrete points we are telling it is I, this is your I plus 1 and this is I minus 1. As we are considering only one dimensional, we are using index I, but if it is two dimensional then we will use index j in y direction, and if it is three dimensional then index k in third direction. So, these derivatives whatever we have written, if f x is a continuous function, then if we need to find these derivatives at in the values of these discrete points, then let us say that this f x varies like this. Okay. So, let us say that this point let us say this is your A, B and C, and at these points you have the values known f I minus 1, f I and f I plus 1. So, we will use now Taylor series expansion just to represent this derivative in some approximate values. So, what is Taylor series expansion? Let us write first. Let us say that f x plus delta x, okay, we need to expand using Taylor series about the point x. Okay. So, if this is your x I, so about the x I we want to expand. So, you will get f x plus delta x, you can write f x plus summation of n is equal to 1 to infinity delta x to the power n by factorial n del n f by del x n. Okay. So, this is the Taylor series expansion of f x plus delta x about x. So, we can expand it as f x plus delta x as f x plus delta x by factorial 1 del f by del x plus delta x square by factorial 2 del 2 f by del x square plus del x cube by factorial 3 del cube f by del x cube, and there will be other terms. Now, if you want to represent this derivative del f by del x, so you can write del f by del x as, so this if you take in the left hand side, then you will get f x plus delta x minus f x. Okay. So, there delta x is there, you divide it divided by delta x, okay. And other terms will be there. So, this side it will go, so it will be minus delta x by factorial 2 del 2 f by del x square minus, so we are dividing by delta x, so it will be delta x square by factorial 3 del cube f by del x cube, and so on. So, you can see that we have represented this first derivative of f with respect to x, okay, about the point x as f x plus delta x minus f x divided by delta x. Delta x is your step size and it is uniform. Okay. So, it is uniform grid. So, these discrete points are known as grid, that we have approximated as the value at point f x plus delta x minus f x divided by delta x, and some other terms are there. So, if you truncate it up to this point, okay, if you truncate it up to this point, so this is the finite difference approximation of this first derivative del f by del x, and as you are using one forward point f x plus delta x, it is known as forward difference approximation. Forward difference approximation. Okay. But we are neglecting the other terms. So, these terms are known as truncation error. So, truncation error, if this is your truncation error, because you have truncated this, after that you are neglecting this term. Okay. So, this is your truncation error. Okay. So, this is the truncation error. What is truncation error? So, you can see that truncation error is the difference between the partial derivative and the finite difference approximation, because finite difference approximation is this one, okay, and this is your partial derivative. So, the truncation error is the difference between partial derivative and the finite difference approximation. So, we can write it here, the truncation error is the difference between partial derivative and its finite difference representation. Finite difference representation. So, now you can see that, so truncation error you can write in this case as minus delta x by factorial 2 del 2 f by del x square minus del x cube by factorial 3 del cube f by del x cube, and so on. So, in this case you can see in the truncation error, the leading term, first term is the leading term. In this leading term, the delta x order is 1, right. So, it is actually the error of this approximation is termed as order of approximation as O delta x. So, this is the notation O. Okay. So, this is order of delta x. So, in the leading term whatever you have this delta x or delta x square. So, whatever is the highest order is there in the first term. So, that is known as order of delta x. So, you can see that if delta x is very small, then delta x will be much greater than delta x square, okay, and delta x square will be much greater than delta x cube. Okay. So, obviously, the first term or the leading term in the truncation error will contribute maximum error. So, that is why the error of this approximation is termed as the order of whatever delta x is there in the leading term. So, now if you write in terms of the index I, then you can write del f by del x is equal to at about point I as f I plus 1 minus f I divided by delta x, and what is the order of approximation? It is delta x. So, this is the finite difference approximation and it is forward difference approximation of the first derivative del f by del x. Now, if you want to graphically represent it, what does it mean? So, if you see in the previous graph, so about this point B, actually you are writing this approximation. So, you are using the point C and B. So, the slope, what it represents graphically, it is the slope if you join the points B and C. So, this is your forward difference. Okay. And at point B, if you want to exactly find the slope of this tangent, what will have? So, if you want to plot it, so it will be just tangent at this point B. So, this is your exact representation of the slope of this tangent, but when you are using forward difference and using a points B and C, so this is your approximation, okay, forward difference approximation. Now, similarly, if we use f x minus delta x, so if you expand it using Taylor series about the point x, then you can write f x plus summation of n is equal to 1 to infinity plus minus delta x to the power n by factorial n del n f by del x n, okay, where plus is if n is even and minus sign will come if n is odd. Okay. So, if you expand it, you will get f x minus delta x is equal to f x. So, minus delta x by factorial 1 del f by del x plus delta x square by factorial 2 del 2 f by del x square, then minus delta x cube by factorial 3 del cube f by del x cube and so on. Okay. So, here now if you want to represent the first derivative del f by del x, so you can write it as f x minus f x minus delta x. So, I have taken del f by del x in the left hand side and f x minus delta x in the right hand side divided by delta x, okay, and this will be this side only. So, it will be plus delta x by factorial 2 del 2 f by delta x square plus delta x square by factorial 3 del cube f by del x cube. Okay. So, if you truncate it up to this, then your finite difference approximation is del f by del x is equal to f x minus f x minus delta x divided by delta x, okay. And what is the order of this truncation error? It is the delta x. Okay. So, you can see that we are using 2 points f x and one backward points f x minus delta x. So, as you are using a backward point, it is known as backward difference approximation. Okay. Now, if you want to represent in terms of the discrete points I plus 1 and I minus 1, you can write del f by del x. So, you can write f I minus the backward point f I minus 1 divided by delta x and order of delta x. So, if you want to graphically represent it, so you can actually join the points A and B. So, you are using point A x I minus 1 and point B x I. So, it will be the graphically representation of this approximation. So, this is the slope using backward difference. Okay. Now, if you want to write f I plus 1 and f I minus 1, you expand these two using Taylor series about point x I, then you will get f I plus delta x del f by del x plus delta x square by factorial 2 del 2 f by del x square plus del x cube by factorial 3 del cube f by del x cube plus so on. So, there will be other terms, and similarly you can write f I minus delta x del f by del x plus delta x square by factorial 2 del 2 f by del x square minus del x cube by factorial 3 del cube f by del x cube. You just write the another term del x 4 by factorial 4 del 4 f by del x to the power 4 plus other terms, and here del x 4 by factorial 4 del 4 f by del x to the power 4 minus so on. So, now if you subtract the second one from the first one. So, if we equation, let us say this is your A and this is equation B, then subtract equation B from equation A. Okay. So, subtract equation B from equation A. So, what you will get? So, if you subtract it, then it will be f I plus 1 minus f I minus 1 in left hand side. So, first term will get cancelled, then you will get 2 delta x delta f by delta x. This third term will get cancelled, then fourth term you will get plus 2 delta x cube by factorial 3 del cube f by del x cube and so on. Okay. So, now if you want to represent this derivative del f by del x about point I, then you can write f I plus 1 minus f I minus 1 divided by 2 delta x, and the truncation error will be minus. So, it will be delta x square, because we have divided by 2 delta x divided by factorial 3 del cube f by del x cube and so on. Okay. So, you can see if you truncate it here, then you are actually using 2 points f I plus 1 and f I minus 1 while finding the derivatives at point I. Okay. And the leading order term is having delta x square. So, your truncation error order is delta x square. So, you can write del f by delta x I is f I plus 1 minus f I minus 1 divided by 2 delta x, because these are separated or by a distance 2 delta x. Okay. So, this is your I, this is your I plus 1, I minus 1. So, f I plus 1 minus f I minus 1 divided by 2 delta x, and order of accuracy is delta x square. Okay. So, graphically if you want to represent it, so you are using point x I minus 1 and x I plus 1. So, that means A and C. So, if you join these 2 points A and C, so it will give a slope using central difference, okay, because that approximation is known as central difference. So, you can see that central difference approximation is close to the exact solution of this delta f by delta x. So, this approximation is known as central difference approximation. Okay. So, now if you want to find the second derivative approximation, okay, del 2 f by delta x square. So, you can see from these two equations. So, if you add this equation A and B, then what you will get? So, adding equation A and equation B, what you will get, to just see. So, it will be f I plus 1 plus f I minus 1 left hand side, in right hand side first term 2 f I, the second terms will get cancelled, then you will get 2 delta x square divided by factorial 2 means 2 del 2 f by del x square, and in this case this 2 will get cancelled out, and then fourth term will get cancelled, then the next term will be 2 delta x to the power 4 by factorial 4 del 4 f by del x to the power 4 and other terms. So, here you can see, now if you represent this second derivative of f with respect to x, so you can write del 2 f by del x square. Okay. So, you can write f I plus 1 minus twice f I plus f I minus 1. Now, you divide by delta x square, okay, and the first term will be 2, as you are dividing by delta x square. So, it will be 2 delta x square by factorial 4 del 4 f by del x to the power 4 and other terms. So, the leading order term in the truncation error is order of delta x square. So, you can see that this is the order of delta x square. So, it is a second order accurate. So, del 2 f by delta x square you are representing using 3 discrete point values, one is f I, f I plus 1 and f I minus 1, and this approximation also is known as central difference. So, central difference approximation of this second derivative. Okay. In other way also you can derive this second order approximation. So, that let us see in the next slide. Say you have these discrete points, this is your uniform grid. So, it is I, this is your I plus 1, this is your I minus 1, and you have in between these two, let us say this is your I plus half and this is your I minus half. Okay. So, if you want to represent this second derivative, so you can write del 2 f by del x square. Okay. So, you can write del of del x of del f by del x. Okay. So, you can write del f by del x, you can use a central difference. So, I plus half minus del f by del x I minus half. So, it is your central difference, okay, about the point I divided by. So, what is the distance? So, if this is your delta x, this is the step size, this is your delta x, and the distance between these 2 points are also, the distance between these 2 points is also delta x. So, this is the first derivative you are writing, and so you can write delta x, and what is the order of accuracy? So, we have seen that it is second order accurate. So, it will be order of delta x square. Okay. So, now you can see that del f by del x, now you can again use central difference, okay, of this. So, you can write del f by del x at I plus half. So, this is your I plus half. So, this point is I plus half. So, this if you use the central difference, then you will get f I plus 1 minus f I divided by delta x. So, it is the central difference approximation of the first derivative. So, f I plus 1 minus f I divided by delta x about the point I plus half. So, what will be the order of accuracy? It is delta x square and minus del f by del x about point I minus half. So, about this point you take the central difference approximation. So, you will get f I minus f I minus 1 divided by delta x, and these two approximations also delta x square, earlier it was also delta x square. So, order of accuracy of this approximation will be delta x square. So, now you can write it delta x square. So, it will be f I plus 1 again minus twice f I. So, plus f I minus 1 and order of delta x square. So, this way also you can derive the finite difference approximation of the second derivative of f with respect to x. Now, let us see that if you use more than 2 points for the first derivative, then in forward difference and backward difference how you can write. So, for this let us say that we will use 3 discrete points. Okay. So, we will find the value of del f by del x. Okay. So, this is the finite difference approximation of del f by del x using 3 discrete points, and we will use f I plus 1 and f I plus 2. So, using f I plus 1 and f I plus 2. So, we are using forward points I plus 1 and I plus 2. So, it is forward difference approximation, forward difference approximation. So, we will use a uniform grid. So, the spacing between these points I plus 1 and I plus 2, let us say, so this is your I, this is your I plus 1 and this is your I plus 2, and it is uniform step size. So, it is delta x and this is also delta x, and the values at this point f I plus 1, this is f I plus 2 and this is your f I. So, we need to represent this first derivative del f by del x using the values at discrete points I plus 1 and I plus 2. So, first we will use Taylor series expansion of f I plus 2 and f I plus 1. So, if you write f I plus 2, okay, so it is f x plus 2 delta x. So, you can write f I plus 2 delta x del f by del x plus 2 delta x square by factorial 2 del 2 f by del x square plus 2 delta x cube by factorial 3 del cube f by del x cube plus 2 del x to the power 4 by factorial 4 del 4 f by del x to the power 4 and other higher order terms. So, now let us expand f I plus 1 about the point x I. So, you will use f I plus 1 is f I plus delta x del f by del x plus delta x square by factorial 2 del 2 f by del x square plus del x cube by factorial 3 del cube f by del x cube plus del x to the power 4 by factorial 4 del 4 f by del x 4 and other higher order terms. Now, what we will do? We need to find the values of del f by del x. Okay. So, what we will do? We will just write 4 f I plus 1 minus f I plus 2. Okay. So, we will do this algebra 4 f I plus 1 minus f I plus 2. So, what you will get? So, if you multiply, so if equation this as C and this is your d, then you write 4 into equation d and minus equation A C. Okay. So, if you do that, then what you will get? So, 4 f I plus 1. So, it will be 3 f I. Okay. So, it will be 3 f I. Then you will get, this is your del f by del x. So, it will be 4 into d. So, it will be 4. So, 4 minus 2. So, it will be 2 delta x del f by del x. Okay. Then if you write this term, so it will be multiplied by 4. So, it will be 4 and here 4. So, this term will become 0. Okay. So, this term will become 0 because this is your 4 and this is also you have multiplied by 4 and if you have subtracted. So, this term will get 0. So, next term will be, so it will be plus 0. So, next term you write, so it will be multiplied by 4. So, it will be 4 and this is your 8. So, you will get minus, so it will be 4 delta x cube by factorial 3 del cube a by del x cube and so on. Okay. Okay. So, now you represent del f by del x. So, del f by del x, okay, about point I. So, 3 f I will come this side, it will be minus. So, you can write minus f I plus 2 plus 4 f I plus 1 minus 3 f I, you divide it by 2 delta x. So, it will be 2 delta x and minus. So, this will come in this right hand side. So, it will be plus. So, you divide by 2 delta x. So, it will be 2 delta x square by factorial 3 del cube a by del x cube and other terms. Okay. So, you can see that in this case the truncation error order is delta x square. So, you have represented this first derivative del f by del x using forward difference approximation f I plus 2 plus 4 f I plus 1 minus 3 f I by 2 delta x order of delta x square. So, it is a second order accurate. Okay. So, you have used 3 points f I plus 1 and f I plus 2. So, you are getting the approximation finite difference approximation of this derivative del f by del x as second order accurate. Okay. So, this sometime it is required at the boundary point. So, if you have any boundary and you need to find the derivative, or if you want to apply the boundary conditions in terms of derivative, if you want to have second order accurate of this approximation, then you can use it, because you will get these 3 points as this is your I, this is your I plus 1 and this is your I plus 2. So, if you require second order approximation at the boundary points of first derivative, then you can use this approximation. Okay. So, similarly, if you want to use 3 backward points, so f I minus 1 and f I minus 2, then similarly you can find this derivative del f by del x using 3 values f I minus 1 and f I minus 2. Okay. So, similarly, if you use it, this Taylor series expansion for f I minus 2. So, you have 3 points. So, this is your 3 points, discrete points separated by distance, uniform distance delta x. So, this is your I, this is your I minus 1 and this is your I minus 2. So, the values at this point is f I minus 1 and f I minus 2. So, similarly, whatever way we have derived the forward difference approximation using 3 points, we can use the backward difference approximation, backward difference approximation to find the del f by del x, okay, using 3 discrete point values f I minus 1 and f I minus 2. So, here f I minus 2 you can write f I minus 2 delta x del f by del x plus 2 delta x square by factorial 2 del 2 f by del x square minus 2 delta x cube by factorial 3 del cube f by del x cube and so on. Similarly, f I minus 1 you can expand using Taylor series about point x I. So, you will get f I minus delta x del f by del x plus delta x square by factorial 2 del 2 f by del x square minus del x cube by factorial 3 del cube f by del x cube, okay, and other higher order terms. So, if you do this algebra, let us say minus 4 f I minus 1 plus f I minus 2. Okay. So, that means, if it is your equation E, this is your equation F, then you multiply equation F with 4 and subtract it from C. So, it will be C minus 4 into F. So, what you can write 4 f I minus 1. So, 4 f I minus 2 minus 4 f I minus 1. So, if you multiply this f with 4, so you will get minus 3 f I. Okay. Then you will get here 4 and 4, so you will get 2. So, you will get plus 2 delta x del f by delta x. You can see here the third term in the right hand side will get cancelled, because you are multiplying 4 with f and you are subtracting. So, you will get 0. Then the other term will be here. So, it will be 8 minus 8 plus 4. So, it will be minus 4 delta x cube by factorial 3 del cube f by del x cube and other terms. Okay. So, now if you want to represent del f by del x, okay, so you can write this 3 f I, you can take it in the right hand side. So, it will be 3 f I minus 4 f I minus 1 plus f I minus 2 divided by, so 2 delta x, and this will be in the right hand side. So, it will be, you are dividing by 2 delta x, so it will be 2 delta x square by factorial 3 del cube f by del x cube and other higher order terms. So, you can see the leading term in the truncation error is having the order of delta x square. So, this approximation del f by del x, you are using backward difference approximation and you are using 3 discrete values f I minus 1 and f I minus 2, which is having the order of accuracy delta x square. Okay. Similar way, so you can actually use these for the boundary points to having this first derivative with this accuracy delta x square. So, if you want to use or if you want to discretize any derivative, first derivative del f by del x at the boundary points and you need second order accuracy, then you can use this. You can see this is your boundary. So, this is your I, this is your I minus 1 and this is your I minus 2 and the distance is delta x and this is your delta x. So, till now we have found the derivatives of a single variable. So, now if we want to find the mixed derivatives, so how we will find it? So, mixed derivative means say if f is function of x and y. Okay. So, now you want to find the mixed derivatives of it. So, you want to find del f by del x del y, okay, about any point, let us say I and j. So, I is the index notation in x direction and j is the index in y direction. So, in this case now the grid points or discrete points let us draw. So, it will be on uniform grid we are drawing. So, this is your I j this. So, in right hand side, so it is I plus 1 j. So, this is your I minus 1 j, this is your I j minus 1 and this is your I j plus 1. So, these are the discrete points and we want to find this mixed derivative about this point I j with the neighboring values. Okay. And the distance, these are uniform step size. So, this is your delta x, this is also delta x and this is your delta y and this is your delta y. Okay, so, delta y is also uniform and delta x is also uniform, but delta x may not be equal to delta y. So, in this case we will use Taylor series expansions of two variables. So, Taylor series expansion for two variables. Okay. So, if you write for two variables, you can write this way: f x plus delta x, y plus delta y. So, this you want to expand about the point x y. So, it will be f x y plus delta x del of del x plus del y del of del y f x y plus del x del of del y. So, it will be 1 by factorial 2 1 by factorial 2 plus del y del of del y square f x y and so on. Okay. So, if you expand it, so it will get f x y plus del x del f x y, or you just write del f by del x plus del y del f by del y. So, this is your factorial 2. So, 1 by factorial 2 is 2. So, 1 by 2 delta x square del 2 f by del x square plus delta y square by factorial 2 del 2 f by del y square, and you have del x del y by factorial 2. So, it will be 2 here, here 2 del f del x del y and so on. So, you will have now this 2 will get cancelled out. Okay, 2 will get cancelled out. So, if you now expand all these f I plus 1 j, f I minus 1 j, f I j plus 1 and f I j minus 1, then you can write all these points. So, another points you write here I plus 1 j plus 1, here another point I plus 1 j minus 1, this is your I minus 1 j minus 1 and this is your I minus 1 j plus 1. Okay. So, if you write f I plus 1 j plus 1, so you can expand it using this f I j plus del x del f by del x plus del y del f by del y plus del x square by 2 del 2 f by del x square plus del y square by factorial 2 del 2 f by del y square plus del x del y del f del x del y, and whatever you have neglected. So, that will be order of accuracy as delta x cube delta y cube. Okay. So, now if you write for f I minus 1 j minus 1, similarly you can write f I j minus delta x del f by del x minus delta y del f by del y. Okay. So, it will be plus delta x square by 2 del 2 f by del x square, then it will be plus del y square by 2 del 2 f by del y square, and it will be minus minus plus. So, it will be delta x delta y del f del x del y. Similarly, you can write f I minus 1 j plus 1. Okay. So, it will be f I j, so it will be minus delta x del f by del x plus delta y del f by del y, and it will be delta x square by 2 del 2 f by del x square, then it will be plus delta y square by 2 del 2 f by del y square and del x del y del f by del x del y, and f I plus 1 j minus 1 if you write, then you will get f I j, so it will be plus del x del f del y, sorry this is x, and this will be minus delta y del f del y plus delta x square by 2 del 2 f by del x square plus del y square by 2 del 2 f by del y square plus x del y del f by del x del y. So, here it will be minus and this will be also minus. Okay. So, now if you do this algebra, f I plus 1 j plus 1 minus f I plus 1 j minus 1 minus f I minus 1 j plus 1 plus f I minus 1 j minus 1. So, what you will get? So, you can see, so f I plus 1 j plus 1 minus f I plus 1. So, this is your minus, then this is minus and this is plus. Okay. So, this is plus, this is plus and this is minus, this is minus. So, if you do it, you will see that these f will cancel out. So, if these are 2 plus and these are 2 minus. So, these will also cancel out, these will cancel out, these will cancel out, these will cancel out. So, you will get only 4. So, it is minus minus plus. So, 4 delta x delta y del f by del x del y. Okay. So, if you write it, so it will be order of del x cube del y cube. So, now if you want to find the mixed derivative, so you can write del f by del x del y is nothing but f I plus 1 j plus 1 minus f I plus 1 j minus 1 minus f I minus 1 j plus 1 plus f I minus 1 j minus 1. So, you divide by 4 delta x delta y. Okay. So, what will be the order of accuracy? Because the truncated term whatever we have seen that it is order of delta x cube and delta y cube. So, now we are dividing by delta x and delta y. So, obviously, then order of accuracy will be delta x square and delta y square. So, you can write order of accuracy is delta x square and delta y square. So, this mixed derivative we have found using the Taylor series expansion, but you can also derive it using this way. So, you can write del 2 a by del x del y, you can write it as a del of del x of del f of del y. Okay. Now, you can use the central difference. Okay. So, if you use the central difference, then it will be order of accuracy delta x y square. So, if del of del x, so now we are using del f by del y. So, that we are using f. So, it is at I j. Okay. So, this we are writing. Okay. So, at I j. So, del f by del y you can write f I j plus 1 minus f I j minus 1 divided by, so 2 delta y, okay, 2 delta y. So, what is the order of accuracy? Because we have used central difference of this first derivative. So, you can write order of delta y square. Okay. Now, this you can write 1 by 2 delta y, and now you can write del f by del x about I j plus 1 minus del f by del x I j minus 1, which is order of delta y square. So, now again it is first derivative. So, now you can use central difference, so that it will be order of accuracy will be delta x square. So, you can write 1 by 2 delta y. So, for del f by del x you can write at I j plus 1. So, if you use the central difference, so you can write f I plus 1 j plus 1 minus f I minus 1 j plus 1 divided by 2 delta x. Okay. This is the central difference, and obviously, the order of accuracy is delta x square. And similarly, this you can write del f by del x at I j minus 1. So, it will be I plus 1 j minus 1 minus f I minus 1 j minus 1 divided by delta 2 delta x. So, this is also central difference of this first derivative about the point I j minus 1, and both are having the order of accuracy delta x square. So, overall accuracy is delta x square delta y square. Okay. So, if it is so, now you can write, so it will be 4 delta x delta y, it will be f I plus 1 j plus 1 minus f I minus 1 j plus 1. So, it will be minus f I plus 1 j minus 1, and this minus minus plus. So, it will be f I minus 1 j minus 1, and order of accuracy is second order in both x and y. Okay. Now, let us use forward difference for this mixed derivative. Okay. So, if you use the forward difference approximation, then similarly you can write del 2 a by del x del y as del of del x del f by del y I j. Okay. So, this you can write if you use the forward difference of this first derivative. So, you can write del of del x del f by del y. So, it will be f I j plus 1 minus f I j. So, this is your forward difference divided by the distance between these 2 points is delta y. What is the order of accuracy? This is the first order accuracy, so it will be order of delta y. Okay. So, similarly, you can write now 1 by delta y del f of del x I j plus 1 minus del f of del x I j, okay, and order of accuracy is delta y. So, now you got the first derivative, okay, with respect to x. So, now you use again forward difference for each derivative. So, what you will get 1 by delta y. So, if you use this del f by del x, so you will get f I plus 1 j plus 1 minus f I j plus 1 divided by delta x. And what is the order of accuracy? Obviously, order of delta x, and you will get here f I plus 1 j minus f I j. This is also we have used forward difference. So, delta x. So, order of accuracy is delta x delta y. Okay. So, you will get delta x delta y. So, it will be f I plus 1 j plus 1 minus f I j plus 1. So, this will be minus f I plus 1 j and minus plus. So, it will be f I j, and order of accuracy is delta x delta y. Okay. So, today we have used Taylor series expansion to find the finite difference approximation of first derivative and second derivative. So, first we have learned the forward difference approximation, then backward difference approximation and central difference approximation of the first derivative. Then also we have learned the central difference approximation of second derivative, and also at the last we have learned the finite difference approximation of mixed derivative. Thank you.